Welcome to week two. Week two kind of starts where week one left off. We're going to continue the discussion about heat and energy. Basically, we're going to talk about temperature and how we measure it. And then the second part of week two is really the beginning or the introduction of water and how that relates to the atmosphere. This is a pretty pivotal week, so I want to talk about the high-end topics that you need to pay particular attention to help you avoid getting that is that. So I'm going to just take a quick rundown of some of those topics. Week 2 starts with a continuation from chapters 1 and 2 in week 1. Specifically in chapter 2, when we're talking about radiation and how the atmosphere is heated, we're continuing that on with temperature. So important concept to keep in mind when you're reading chapter 3 is recalling chapter 2. The sun heats the earth heats the atmosphere. Because the Earth is the heat source for the atmosphere, the closer you are to Earth, at least in the troposphere, the closer you are to Earth, the warmer the temperature is going to be. That then makes sense why the troposphere has cooling temperatures with height. If you think back to that temperature profile, and we distinguish layers of the atmosphere by what the temperature profile did, in the troposphere, the temperature is always decreasing with height. The reason the temperature is decreasing with height is because you're getting farther away from your heat source. So things start to intertwine the farther we go into class, so that's one of the reasons to keep in mind there. The temperature profile in the troposphere usually has decreasing temperature with height. That is the normal condition. Now there is a special case that is called an inversion. An inversion is when the temperature increases with height. Most nights across the world, whenever the sun sets, will develop an inversion. The reason an inversion develops is because just like during the day, the atmosphere heats from the ground up, it also cools from the ground up. So the temperature fluctuates most near the surface and least the higher up you go in the atmosphere. So that's why during the day you have cooling temperatures with height, and at night, or sometimes during the day, in what are called stable situations, you can have temperatures increase with height. I wanted to add one more thing about inversions. Inversions can be one of the very cool and very easy things to see concerning the atmosphere. If you've ever gone camping or ever started a fire or maybe just been around a city where there's a lot of smokestacks, have you ever seen the smoke get to a level and then just flatten out in the atmosphere? The pollutants from the smoke, whether that be from your own personal backyard fire, from the campfire, from the factories around town, or maybe some truck pollutant on the highway, whatever the case may be, when you see that smoke flatten out and kind of reach a layer, it has reached an inversion in the atmosphere. That inversion has trapped that pollution and it no longer allows it to rise, and because it no longer rises, it just kind of spreads out, and you'll see the atmosphere get very layered like that. In very polluted areas like Salt Lake City or occasionally in Maryland, you'll see those instances, and that is a very great visual representation of what an inversion is like. There's an interesting aside to have here. When you realize that temperature decreases with height in the troposphere, the height of your measurement matters dramatically for the temperature that you're going to report or tell other people that you're reading. If your thermometer, is at a foot off the ground, you're probably going to read a temperature as much as 10 degrees hotter than a thermometer 10 to 20 feet above the ground because you're so near the heat source of Earth. Imagine that you put your hand really close to a light bulb. So imagine my fist is the light bulb. The closer I get to that light bulb, the hotter it's going to get. The farther away, the cooler it's going to get. A thermometer and the distance it is from Earth's surface works the exact same way. So it's very interesting. The variances that you can get in the temperatures around your area might very well be based on where or how high those thermometers are from the surface. Another consideration to keep in mind is thermometers that are not shaded will typically be 10 to 20 degrees warmer than the thermometers that are shaded. Officially, we take measurements of temperature in the shade because solar radiation will directly heat the mercury or the alcohol that the thermostat is recording, the thermometer is recording. And in those circumstances, we're not measuring the actual temperature of the atmosphere, we're measuring the incoming radiation from the sun instead. So just some interesting points to consider there when you think about temperature and maybe your local news or stuff that you see online. Stuff to keep in mind. A large concept that will be repeated over and over in the class, and you'll have to keep in the back of your mind, is scale dependencies. For instance, temperature has many, many different scale dependencies, depending upon what you're talking about. If you are just watching the video in order, I just briefly talked about how temperature changes based on your height above the ground. That's a small scale difference in the temperature, or those micro differences, those small scale differences in your very small environment, just a couple feet, change the temperature. So that's a small scale example. So just a few feet to maybe 100 yards. The middle scale is something maybe the size of a state. So there's different, states can have different temperatures based on elevation or how north-south they are, even the color of the ground, if there's trees or if there's dirt. And then you can talk about global differences. The North and South Pole are obviously much, much colder than the equator because the angle of the sun changes based on latitude. So the scale dependencies, not just on temperature, but on many things we'll talk about in class, is something to keep in mind. That being said, controls on temperature. The big ones are latitude, elevation, and your proximity to water. Latitude is important because the angle of the sun changes depending on how far north and south you are away from the equator. The elevation matters because not only are you farther away from perhaps your source near the ground, but it's not that as much as you can get extremes in your ranges, extremes in your temperature, meaning that during the day you can get just as hot as an elevation 1,000 feet lower, or at night you can get extremely cold because you're radiating heat so much faster the higher up you are. Then the proximity to the water is probably the most important concept to keep in mind. The closer you are to, let's say, an ocean, the more moderated your temperatures are because the ocean stores heat during the day, so it doesn't allow the temperature to get as hot because it's absorbing and evaporating some of that water away, and then which is a cooling process. And then at night it keeps you warmer because the water is warmer than the land, and that will keep the areas that are right next to the beach, for instance, much warmer. So those scale dependencies are something to keep in mind, and then the three main large-scale, global scale dependencies are latitude, elevation, and proximity to water. The last three things I want to outline about temperature and Chapter 3 are as follows. The first is the misnomer that the hottest part of the day is at high noon, or whenever the sun is at its highest solar angle. This is not true because the Earth continues to warm even though the sun angle starts to decrease. So you go out at noon on the summer solstice, and the sun is at its highest angle, so it's beating down and it's hottest. You can feel the burn, so to speak. But the Earth hasn't responded yet. The Earth hasn't heated up to its hottest temperature, and until the Earth heats up to its hottest temperature, the atmosphere, the temperature of the air, will not be at its hottest. The analogy I use is stick a ham in an oven, turn the oven up to 500 degrees. That ham will start to cook pretty quick. Leave it in there for 5 minutes, then shut the oven off. That ham will continue to heat up even though the oven is off because the temperature of the oven is hotter than the ham. So it continues to heat it up even though the oven temperature has started to set. Hopefully the analogy can kind of help. If it doesn't make sense, I can help you guys out as it goes along. Concept of sensible heat, sensible weather, sensible moisture. Anything sensible just means how you feel it. So sensible weather is just our perception. And it is true that everybody perceives the weather slightly differently. So sensible weather can be a bit abstract and a bit relative. So keep that in mind. But that's what is meant by sensible weather. Lastly, Chapter 3 just talks about how we measure how we measure temperature, how we measure the heat, and how we measure the energy of the atmosphere. Remember, temperature is just a measure of the energy content of the air. There are the main ones are Fahrenheit and Celsius, and then scientifically we use Kelvin. Kelvin is the absolute scale. At absolute zero, which is 0 degrees Kelvin, there's no motion for the molecules, so the molecules are absolutely still and no molecular motion.